We move on to Molecules in Action, Unit 2, Section 3. What is going on between these molecules and our receptor sites that allows us to smell the smells we smell? Let's take a look at this. There's something to do with what is polar and what is nonpolar. What does that mean? Well, let's take a look at this list here. This list shows us that all of these are polar. Let's see. Water molecules, vinegar, nail polish remover, rubbing alcohol, and antifreeze. Then there are the nonpolar molecules, which look like mineral oil, hexane, paint thinner, and motor oil. Let's look at the difference. Well, to understand all of this, we have to consider the Molecules Attract lab that we did earlier in the semester. Notice that a water molecule has oxygen here and 2 hydrogens, and because oxygen has a stronger pull for electrons, this end of the water molecule is negative and the other end is positive. We know that if water lines up in a stream, it is going to look like very much like this picture here, and that if we bring a charged wand close to that stream of water, that water will attract to the wand, and our explanation was that water had charged particles. The charged wand, now knowing that it has been charged with electrons, will pull the positive ends of the water molecules toward it. A little cartoon in section 2.16 helps us with looking at the different types of molecules in terms of electronegativity difference. So we think of it as a struggle for the ice cream cone, if you will, where the ice cream cone represents the electrons and the polar bear and the penguins represent the elements within the molecules. So if you can imagine, if you have 2 oxygen atoms or 2 hydrogen atoms, you have nonpolar covalent molecules because there is equal sharing of electrons. Polar covalent is where there is unequal sharing, for example, between the penguin and the polar bear. The polar bear is going to, being more electronegative or being able to pull on electrons more, is going to get more of the ice cream or more of the negative end, and we show this by drawing this arrow. This is the negative end, this is the positive end. The most extreme case of sharing, or in this case not sharing, would be the ionic bonding, where literally the polar bear, for this particular cartoon, is so electronegative that it is able to pull the electron away from the metal, creating a negative ion and a positive ion. Now, this brings up the electronegativity scale, which I may have mentioned. Linus Pauling came up with a way to measure how well an atom pulls on electrons. In this case, the scale is from 0.7 to 4, with this area being the least electron pulling, so the metals, and the nonmetals in this area being the greatest electron attractive. So if you just recall that, you're all set. This last group does not attract anything because they're already stable. So you can take 2 atoms, look at their electronegativity difference, and automatically tell what kind of bond is being formed. The greater the difference, the stronger the bond, the more polar it is. In section 2.18, we connect polarity to smell. So we can say that polar molecules have a smell and nonpolar molecules do not. The theory is that the polar molecules have an attraction to the water that's in your body, and so we are able to transport that smell. It kind of sticks to the water in your nasal passages, and we're able to transport that up through the receptor site. So, summarizing it, we can say that we know from previous sections the different bonding types. We can say that most of these do not have smells, with the exception of some of the non-metal type molecules. The ones that, of these, the ones that probably smell are the ones that are polar. Okay. And as a second summary, we can also summarize it by saying that in terms of connections to smells, small polar molecules have a tendency to smell. Some of the medium-sized particles also can be smelly. Most of them are gases and liquids, as these are able to be easily evaporated and absorbed into the nasal passage and the nerve receptor sites.